Hello and welcome. Today we're diving into an invisible force that connects something as simple as an electrical wire to something as powerful as a magnet. And believe me, this connection doesn't just explain how our gadgets work, it literally shapes the world around us. So what's the big secret?
So let's start with that big question. What on earth does a simple electric wire have in common with a powerful magnet? Well, the answer is surprisingly deep, and it all boils down to this invisible field of influence that they both create.
And that field is, you guessed it, a magnetic field. Now, the best way to think about it is like an invisible spider's web. A magnet, or a wire with current flowing through it, is basically spinning this web out into the space all around it. You can't see it, you can't touch it, but if another magnetic object gets too close, it gets caught and pulled in. It's true action at a distance.
All right, so here's our game plan for piecing this all together. We're going to start by uncovering a current's secret identity. Then we'll figure out how to measure this invisible force. After that, we'll look at a really elegant shortcut. From there, it's off to a cosmic dance of particles. And finally, we'll see how all this theory powers the tech we use every single day.
Okay, first up, a current secret identity. This is the big one. This is that foundational aha moment that really kicked off our entire understanding of what we now call electromagnetism.
You know, it all started with a really simple observation. If you run an electric current through a wire and bring a little metal nail nearby, it sticks, just like a magnet. This proved something absolutely revolutionary. An electric current isn't just a flow of energy, it's a source of magnetism. That wire is generating its very own invisible web.
So we know this field exists. That's a huge step. But for science, just knowing something exists is never enough. The very next question is, well, how strong is it? How do we put a number on it? And that brings us to our first major tool for the job.
And that tool is called the Biot-Savart law. I like to think of it as the official rule book for the magnetism you get from a current. It gives us a precise mathematical way to calculate the strength of that magnetic field at any point in space created by even a tiny, tiny piece of a wire. Now, I know this equation might look a little intimidating, but trust me, it's really just a recipe with a few key ingredients. First, the field strength depends on the current, I. Makes sense, right? More current, stronger field. It also depends on your distance, R. The field gets weaker the farther away you get. And finally, the angle you're looking at it from matters too. The field is actually strongest when you're at a perfect right angle to the wire. So, the Biot-Savart law is awesome, it's fundamental, but the math can get pretty hairy. Luckily, for certain situations, physicists came up with a much more elegant approach. A powerful shortcut, really, and it's called Ampere's law. Ampere's law gives us this really beautiful insight. Imagine you could just draw an imaginary loop, a path, in the space around a current-carrying wire. Ampere's law says that if you were to walk along that entire closed loop and add up all the magnetic field you experience, that total is directly tied to the amount of current punching right through the middle of your loop. So why is this so great? Because for situations that are really symmetrical, think of a super long straight wire or a coil shaped like a slinky, it turns what would be a really gnarly calculus problem into something you can solve with simple algebra. It is the physicist's favorite life hack for these kinds of problems. All right, so we've spent a lot of time on how currents create magnetic fields. Now let's flip the script. What happens when a single charged particle, say an electron, goes flying through a magnetic field that's already there? This is where things get really, really dynamic. So picture it in your head. A single lonely particle is zipping through space. Then, suddenly, it enters a region with a magnetic field. What happens to it? Does it keep going straight? Does it slow down? Or does something totally different happen? Well, it turns out there are two main possibilities, and it all depends on the angle it enters at. If that particle's path is perfectly perpendicular to the field, the magnetic force grabs it and pulls it into a perfect, clean, circular orbit. But if it comes in at any other angle, it gets pulled into this beautiful corkscrew shape, a helical path. And the force that's causing all this guiding force, has a name, the Lorentz force. So how do we know which way the particle is going to get pushed? Well, physicists have a super simple trick for this. It's called the right-hand rule. You can even do it with me now. Point your thumb in the direction the particle is moving. Now point your fingers in the direction of the magnetic field. The direction your palm is pushing, that's the direction of the force. It's a fantastic, instant way to figure out the direction of this cosmic dance. Now, all this physics is absolutely fascinating, but what's the point, right? How does this affect us? Well, in this final section, we're going to connect these deep, fundamental forces to some real-world technology that you've probably seen or even used.
That exact same Lorentz force that makes a particle spiral through space, that is the engine inside a really key device called the moving coil galvanometer. It's basically a super sensitive tool that uses that magnetic push on a wire to detect even the tiniest, faintest electric currents.
But a galvanometer on its own is almost too sensitive for everyday use, so we have to upgrade it. To turn it into an ammeter, which measures large currents, we add a path of really low resistance next to it, in parallel. It's called a shunt, and it lets most of the current just bypass the delicate parts. To make a voltmeter, you do the complete opposite. You add a high-resistance component in series, which makes sure it draws almost no current at all so it can accurately measure the voltage difference between 2 points.
Just stop and think about that for a second. The very same invisible force that guides a cosmic ray as it spirals through our planet's magnetic field is the exact same force we've harnessed to make the needle move on a meter in a lab. It's just a perfect, beautiful link between the cosmic and the practical.
So we've come full circle and established this fundamental truth. A moving charge, a current, creates a magnetic field. But this leaves us with one last, really tantalizing question to chew on. If moving charges create magnetic fields, what happens if you do the reverse? What happens if you take a magnetic field and you change it right next to a stationary wire? Well, that is a story for another time.